Hey everybody, we're here to give you another model walkthrough of the cadCAD model for conviction voting that was carried out between Block.Science, Aragon, OneHive, and the Common Stack this past month. A couple of quick introductions. This is Andrew Clark, data economist at Block.Science and also the lead system modeler on the conviction voting model. And I'm Jeff Emmett. Here's the Aragon conviction voting repo. You are more than welcome to dig through and see everything that's going on behind the scenes here. This is basically, a new cadCAD best practice model. So if you are interested in cadCAD modeling in general, it's definitely useful to take a look through the structure of this notebook and how everything is set up. But first, we'll go a little bit into conviction voting from a higher level. So you can see all the various notebooks that we've got here. Starting with the README doc, which is exactly where we are. So first, a bit of background information. So Andrew, maybe you can tell us briefly what this cadCAD model does.
Sure thing. cadCAD models are built to represent reality in the same way as you would think like a flight simulator or something like that to represent how an airplane functions of the dynamics. We call them digital twins of an economy or a type of network or socioeconomic social network, for instance. And the goal of these systems is to replicate as closely as possible so we can stress test and find the optimal design. For normally economic systems, it's very much just kind of haphazard, theory-based, which a lot of times the theory is simplified to not represent reality at all, such as rational actors and economics. In real engineering fields, structural engineering and things like that, nobody would ever build a complex bridge without stress testing it and making a simulation and seeing where it will fail. And that's what the cadCAD framework is bringing, is some of the strong physics and engineering principles we're being able to bring into more areas for economic modeling and community modeling and things like that by being able to create these digital twins, as this graphic can illustrate here.
Awesome. And since we're experimenting with new forms of community governance, voting, and how that evolves in a complex adaptive system, this basically gives us better oversight into how these various components may impact our system in ways that we don't necessarily, it's not intuitive to us. Is that correct?
Correct.
Cool. Awesome. So a little bit about conviction voting. So conviction voting is a novel form of governance. It's basically like real-time vote streaming. But actually, we have some interesting realizations. It moves kind of beyond voting to preference streaming. So a little bit of interesting background on voting. I mean, it's quite a difficult problem because what we're trying to do is take private, distributed, continuous, and time-varying signals from a community and turn them into public, centralized, discrete events, as in yes, we will do this, or no, we won't. So this is ultimately a signal processing transformation. And the way that we, traditionally collect votes through a yes or no, checking a box on a piece of paper and counting it up, is, quite old school, and I mean it's with new technology that's available to us through blockchain and Web3, we can start to move past that and actually get these continuous signals from a community that can foster collective intelligence. But of course, this is a very complex issue. As soon as you involve voting and governance, there's a lot to consider. We have to consider what rights these tokens give us, and how you get access to those rights, and how those are managed both now and into the future. So there's a lot of considerations when we get into conviction voting as to how it should be set up, who has the right to vote, what say should they have, how are votes counted, etc. There's also a few different flavors of conviction voting, and the one that we're looking at primarily in this notebook is the a proposal that has a threshold that is passed. So essentially, people who hold tokens can vote on proposals. They don't actually send those tokens anywhere. They stay with the user, but they charge up this battery almost of conviction. And when that battery hits a certain threshold, like a neuron firing with an action potential, actually this is very similar to how decentralized decision making is made in nature, the proposal passes or it fails. There's a different flavors of conviction voting. So basically this is rich design space And there's lots of area to explore how this new voting tool, these new governance tools can be used for collective intelligence. So there's a bit more on conviction voting in this notebook. You're more than welcome to dig into it. There's a couple of really interesting conviction voting experiments ongoing at the moment. One Hive has conviction voting deployed in their DAO. Actually, Aragon just launched their conviction funding experiment. There's a common simulator undergoing with the Common Stack project at the moment. So all of these are definitely worthwhile experiments to check out with regards to conviction voting. So that's a pretty high-level overview. If you want to dig more into, the derivations of these algorithms, actually we have a couple of notebooks that dig right into the mathematical derivations. So of course, when we're engineering systems, we need to make sure they're robust. We need to make sure that we've understood all of their failure modes. And of course, engineering and modeling anything has to start from mathematical first principles. So you can see here a couple of the, or maybe Andrew, maybe you can give us a quick run through what these like bipartite graphs mean and how we basically get these preferences from participants for proposals.
Definitely. So the underlying structure to this simulation model is from graph theory. It's a branch of mathematics that represents everything in graphs. So a digraph is a graph that has two main components, in this part, participants and proposals, and can have, these are two types of vertices or nodes. And then what interacts those lines between them are called edges, which are what connects. And you can have multiple edges per different participant. But what you have here is you can have such as affinity for a proposal from a participant, or 1 means they highly, highly, highly like this proposal. -1 means they highly, highly, highly dislike this proposal. And then that's one edge. And then the amount of tokens that they have committed to this proposal is another edge that's connecting the participants and proposals here. On the support for the proposals that they have there when they're supporting with their tokens that are pledged. It's the types of interactions in between these participants and proposals that we're modeling here, and where all of the logic can be embedded in these edges and vertices here for the different amount the amount of conviction required to pass a proposal, the amount of tokens an individual holds. All of these are types that can fall under those vertices and nodes of participant and proposals.
Right, and we're basically engaging in computational social science here, where we create graphs and we can actually represent, the influence networks or the social network effects of, say, this node is Andrew and this node is Jeff, and Jeff has a very high opinion of Andrew's, estimation of what needs to be done in this community. Andrew will have a high influence on Jeff's decision making in which proposals to support. So there's a whole lot of interesting, social effects that we can model through graph theory. And same thing with proposals. There are some proposals that may be in direct conflict. Maybe two proposals are out there to do the exact same thing, whereas other proposals may have very strong synergy. One much facilitates the other, so we can really get a good understanding of the social dynamics using these graph structures. And again, there's a lot more mathematical derivations here. If you are of that bent, please feel free to dig in. There's a deep rabbit hole of the mathematical formalizations, and of course that's what brings the rigor to these models. We've also identified some of the important considerations when you're deploying conviction voting. So, one of the audience that may be watching this video are people who are interested in deploying conviction voting in their system. So there are a lot of considerations. Maybe Andrew, you can pick one or two and just give a quick introduction of what may need to be considered when using conviction voting in your system.
Definitely. Timescales is the first bullet here, and it's one of the most important ones. As some implementations, such as the Argonne one that we're reviewing here, is based off of blocks. How often those blocks are finished up in a blockchain network will be the scales for the alpha life cycle, for instance, on how quickly it will decay. So there's a bunch of logic around those things. So it could be hours, days, blocks. For us, we're doing everything in days. So we had to do some calculations from alpha to derive the difference between those. But it's a very important thing for you to update if your network may update by the hours. Well, cadCAD can definitely support that, but you're going to have to go and check the logic on those sorts of things. Same with the candidacy times. For example, in our simulation here, we're saying a proposal has to exist for 1 day at least before it can pass. So even if it has a lot of conviction, we're wanting to see staying power. So like if you're trying to do a presidential election, for instance, 1 day liking a candidate is probably not good enough. You may want to have 30 days, 2 months, something like that. So these are the types of the logic that you really have to start worrying about. Same with beta and rho are 2 parameters that are in the simulation, along with alpha, and there are certain ways we can tune those with the cadCAD simulation, such as A/B testing and parameter sweeping a range of values, that those have a high impact if you read some of the documentation on like the trigger function and things on what constitutes passing proposals. So this is a great template if you're doing conviction voting of where to start, but definitely dig into the details, read these documents here like the trigger function and things to see how the underlying mathematics work, to know what you should optimize for your implementation. Like here's some math right there that Jeff was just showing. They're very much, you need to look at the assumptions, read all the documentation, and see what needs to be changed, because it's right for our implementation and matching what the Oregon folks are doing and for their implementation may not be what's optimal for you. So the mechanics are here, but the parameters need to definitely be adjusted to your use case.
Right. So this could almost be seen as like a foundational building block. Of course, this model needs to be customized for, you know, a specific implementation, but a lot of this work can be reused and reparameterized for, you know, various situations with slightly different trigger functions or slightly different, you know, minimum proposal times, or yeah, basically this is sort of the groundwork that can be built upon to add additional functionality and suit additional use cases. Awesome. Okay, so we've got, yeah, as Andrew mentioned, there's a whole bunch of other notebooks to dig into, deriving alpha and looking at some of the parameters of conviction voting. Definitely check out these notebooks. But the main notebook here is our V3 simulation notebook. So Andrew, I'll turn this over to you and let you, you know, introduce a couple of concepts from here. So this is basically where we run most of our rigorous modeling of the conviction voting system.
Mm-hmm. Yes. So in this example here, we're just introducing the alpha and things like that. Let's go a little bit lower of how everything works in a stock flow diagram, which is essentially you're looking at 2 different types, such as the stream of water through a faucet, and then the basin of how much is in that result, are kind of like the basis of how these simulations work for the different time steps. Is this your bank account, or is this the amount of money you spent during a month, for instance? So the cadCAD model structure, that's how the systems dynamics is the basis for the types of modeling we do, which is unique versus like machine learning or types of models like that. So an example here, Jeff, if you'd change tabs there, yeah. There you go, perfect, is the cadCAD model structure. So the cadCAD model structure, we have several different components to it. And we have another doc that goes into it in more detail that we're going to link to right here. Jeff, if you wouldn't mind just pushing on that.
Sure.
Perfect. This can serve as a template for other projects you want to do in cadCAD as well. There's 4 levels to cadCAD, where there's behaviors, which are the kind of the logic, the higher level. If an agent is interacting with the system, what are their decision types going to be, for instance? And then the mechanisms, which are actually just the route processes of updating the state variables based off these decisions. The state variables could be what is your bank account value today, and then what's the amount of change in your bank account. Those could be 2 separate state values. And for instance, if the behavior is, as a rational actor, are you going to spend money or not on this widget? Then it will flip, the mechanism will update based off the decision, the state, and will update your bank account and the amount of money that changed based on that example. And then metrics are that 4th layer down there at the bottom, which will show the aggregate state of the system, such as like how much money did you spend during this month as an overall system health, and what amount of assets do you have versus your liabilities, or what's your health of your bank account essentially going forward, are what we can kind of use in the system to help us understand the health of the system. So the file structure of how we build these simulations, there's a couple key components, which is the configuration, which says like, am I running how many Monte Carlo runs, how many time steps? For our examples here, we're using 100 days with, you know, you have to have a minimum of 1 day for proposal. Partial state update block is what's wiring together what we saw in that graph a little higher, which is the behaviors, mechanisms, states, and metrics. And run is what actually runs the simulation. And state variables is where we define what those variables starting values are. For instance, your bank account may be starting at $10. The amount that you spent over the month, 0, because we're starting the simulation, for instance. State schema is just a way for us to verify that if we say that a value is going to be an integer, such as 0, 1, for instance, we verify that that actually happened when we run the simulation. And in our actual simulation, we have 4 components. So there's 4 components: behavior, state, mechanism, metrics. There happens to be in the system as well 4 components to the system. So system, which is the underlying bipartite graph we talked about of participants and proposals, and how that generates over time, such as new participants joining the system, new proposals joining the system, those sorts of logic. Then participants, which is the behaviors and mechanisms and states for the participants, such as this participant decided because the affinity for a project was a certain amount, I'm going to commit this many tokens that I have. Proposals is the logic of, okay, I got enough conviction, I got enough tokens committed to my project, I'm going to pass it. And the different life cycle things there. And then metrics in this case is showing what stages are funds in, how many proposals have passed over the past month, those sorts of basic things. And in this document, we walk through exactly the schema of the states and things like that. But Jeff, if you wouldn't mind going back 1 page, we'll start looking at some of the simulation results. After all of this is run, highly recommend you go and read all of this documentation and for understanding, but we're just trying to give the high-level overview here. We're showing here, before the simulation is even run, we're showing the initial parameters, initial state variables. We're explaining what the different parameters mean for our implementation. We can show the initial participant starting values of their tokens, the amount of honey they have. The initial social network, like Jeff said, which is how influential is this person. We have very rough social dynamics around those sorts of things. And then the amount of funds requested for the different proposals. And their identifiers here, as we had a couple that we started with, and the initial affinities between participants and proposals, which is the amount of the participant A likes proposal Z, for instance. And then we can finally run the simulation, and then we verify the schema that everything's doing what we thought it was going to do. We're looking at the resulting data frame. Everything comes out in pandas data frames, which is very common in data science for processing and things. And we can do some basic plotting here, such as like sentiment over time. You can see that over time, the overall sentiment of the participants, it started at 0.6. It went very high to everybody's very enthusiastic. Something happened for people to not be enthusiastic about the system. Maybe a key proposal didn't pass, something like that, and then it goes back up again. So we have a random dynamic generator in here that acts a lot like things we've seen in social science research, but of course these things can be tuned to your implementation as well. We see the difference between funds and candidate funds, how it changes over time, where those funds are. We can look at the actual affinity between participants and proposals for the whole simulation, which is really cool because on this side, on the left, you have the proposal IDs. And as you see, we started at proposal ID 30, and we've gone all the way up to 193. So there's lots of dynamics coming in here. And some of these proposals are passing, some of them aren't. And then the participants are on the x-axis there. Then we can see the proposal statuses here. So we can see there's been a lot that have been killed is red, completed is green, so that's growing as well. And then candidate is blue, so there's been a big, huge uptick at the end of the simulation here on new things being there. And then there's failed and things as well. So you can see the dynamics of the system and how it's expanding over time as more participants and proposals are happening, and seeing that there's actually being successful proposals passing. And you can see here as well the amount of funds that have been requested, those sorts of dynamics. So a little bit lower here. Yes, we can see that that bipartite graph that essentially we showed early on, just very roughly. This is a plot that shows how is this working in the real simulation. So we have participants on the left, proposals on the right, and it shows what percentage of the conviction required to pass this proposal has been achieved. So this is the beginning of the simulation. Those are the active proposals. And the one below here in this graph, we can see the simulation's a lot farther along. This is time step 50. We can see a lot of proposals are active here or been getting close to being passed. There's one proposal with 125% conviction, which means it should be passed any time now. There's just, you can see at any time step, you can see this interaction of these agents and graphs. So the amount of logic that we have here using these graph objects in in-memory graph database, we can represent a lot of complexity and show this varying over time that you can't do with traditional agent-based modeling or machine learning or econometrics type analysis.
Awesome. So basically what we're seeing here is this system, once we hit go, it's kind of a generative, agent based, like new proposals are coming, new candidates are saying whether they like and support these proposals. We're seeing these proposals pass, some of them fail. So basically we're creating that digital twin of the real world system so that we can see, proposals, coming up in the conviction voting algorithm and getting passed by community support, and then being able to see all of the dynamics in this community in terms of, what funds are available, what funds are requested, and how this would play out in the real world. Is that basically what this is showing us?
Yes.
Awesome. Very cool. And yeah, so as we mentioned before, this is kind of the first iteration of this notebook. There's a lot more functionality that could and will be added. For example, having a Uniswap instance where users can buy more or sell out of the economy. We could also tie this into a bonding curve rather than just a traditional inflationary token model like Bitcoin. And yeah, there's a lot more that we can do with these models to contextualize them to specific instances. We're speaking to a lot of different audiences with this model. For developers who want to use cadCAD, you can definitely fork this model, use it as a template to understand cadCAD best practices and also add additional functionality for your use case. For people who are looking to deploy conviction voting, this is definitely a great repo to learn more about the tool and how it can be used for collective intelligence in your community. And for supporters of this work, there's definitely a lot more research and development that can go into this model. So if we have a funding call out on the bottom of the README, if anyone is interested in supporting this work, or if you're interested in deploying this for your specific community and need help doing modeling and contextualization, please feel free to reach out to info@Block.Science, and we'll include some of those links as well in the YouTube video below. So that's all for today. Thanks very much for joining us in this walkthrough, and we look forward to the next one in a couple of weeks.